Quantitative Aspects of Risk. After we have already some knowledge about what risk is and what risk management is, now we have to go to some technical aspects, starting with the quantitative aspects and the quantitative analysis of risk. For this part of the course, we're going to use a bit more visualization because the terms otherwise are a bit technical. What quantitative risk analysis is? It is analysis of numbers and the probability and the consequence of each risk. Probability distribution analysis is the most popular approach, although there are two other approaches. One is the so-called decision tree analysis and the other is the so-called expected value analysis. The three of them are very important, and now we are going to pay some attention to all of them. So starting with the expected value analysis. Looking at the screen, we can see a very simple case where we have three possible outcomes out of a given situation. In this case, it's about investment in building a property, and we can see that there is an optimistic outcome, a likely outcome, and a pessimistic outcome. The optimistic outcome basically has the cheapest option. The likely outcome is middle of the way option, and the pessimistic outcome is the most expensive option. On the other side, the most likely outcome refers to the highest probability, and the optimistic outcome refers to part of the residual probability, and of course the pessimistic outcome sums all the probabilities up to 1, which is, if you remember, an important feature when we're dealing with probabilities. So all the probabilities here sum up to 1. So what do we do from now? We have three possible outcomes, we have number values, we have their probabilities, and what do? We simply multiply the outcome by the given probability, and we get a weighted result for this given outcome. And when we get this multiplication for all these possible outcomes and we sum everything, we derive the so-called expected value. And in this case it happens to be $243,000 US. If you remember, we have started with the most likely outcome at about $225,000. We had a very optimistic outcome of $150,000, and we had a very pessimistic outcome of $300,000. And you can even see that the pessimistic outcome is slightly more probable than the optimistic. Basically, what we do is a weighted average of the outcomes, and the weights that are used are the probabilities. Next way to analyze risk is the so-called decision tree. Decision tree is basically a graphical representation of what would or what should occur among the outcomes and what are the probabilities of doing so. So in this case we have a slightly a complex decision tree where we have one layer of decision nodes and then we have another layer of decision nodes, but basically it is as if we had the previous situation. We have possible outcomes, combination of nodes, we have a numerical value for each outcome, and we have some sort of weight. In this case, because it is a bit complex, as I mentioned, this is actually conditional probability, but it doesn't really matter. We have some sort of graphical representation of what we should expect, and we have more or less the same approach calculating the expected value, but now it is a bit more analytical. We can see much of the analysis. And the third and most important and most widely used approach is the probability distribution. This is the probability distribution approach. This is, of course, a tool that is widely used across science, across research, in statistics and in mathematics and in risk management as well, obviously, in investment as well. I'm just going to give you here a brief reminder that there are, for each probability distribution, there are 4 parameters that are situating it. It is the mean, dispersion, skewness, kurtosis, and what each of them means is that, first of all, the mean of the probability distribution basically shifts left or right, so locates the distribution at the right place. So this is basically the mean here. This would be the mean, this would be the mean. And if it is a bit to the left or to the right, it moves the whole probability distribution. Then it is the dispersion. It is how wide or how narrow this probability distribution is. Then we have the skewness, which means the asymmetry of the distribution. We are mostly going to deal with symmetrical distributions in our course, but it is not necessarily the case every time. And kurtosis basically gives the shape of the distribution, whether it is more like a trapezoid or whether it is more like a tower. So after this quick reminder, let's move on. So expected value, as we said, is the probability weighted average value of a given variable across all potential scenarios. And uncertainty is the mean absolute deviation from the expected value. The uncertainty includes both sides, the upside and the downside uncertainty. And the uncertainty is typically perceived as a symmetrical distribution, which means there is always balance in the uncertainty. We don't know, symmetrically, we do not know enough in both sides. Let's do a little bit of an exercise here. Let's assume that we have a die, a 6-sided standard die. What would be the expected value of this die? I would like to remind you that there is the numbers of 1 to 6. Only one of them could possibly turn out as an outcome, but there are 6 possible outcomes. So I would like you now to pause this video and think about it and try to calculate the expected value of a die, of a single die. Okay, now that you have tried your best for the last several minutes to calculate the expected value of a die, let's see how it should be done. First of all, we have 6 possible outcomes. Each of them has equal probabilities to be realized. So, this means that the probabilities is always 1/6. And then we have the values of each die: 1, 2, 3, 4, 5, and 6. And if we multiply it and sum everything, this is actually a sum, we will reach to the conclusion of 3.5. So you may ask, how is this possible? A die cannot be 3.5, it could be only 3 or 4, it cannot be 3.5. Well, in our case it is possible, first of all, because we are speaking about very symmetrical distribution. Second of all, a distribution where there is no distinctive mean, and it is basically called a level distribution. You see, all the probabilities are equal, and since they are even in number, 3.5 is equally distant from 3 and 4, and at the same time from 2 and from 5, and at the same time from 1 and from 6. So basically, 3.5 is the expected value of a die. But at the same time, I would like to remind you, it is a non-possible value. It is a non-possible in reality to be achieved. This is the expected value. It is a special feature of events, in this case of a value. So now that we have computed a single die, let us try and compute what is the expected value of 2 dice. I would like you to pause this video and try to analyze the situation and try to derive the expected value of 2 dice. I would like to remind you that there are actually special types of combinations here, and I would like to remind you that you should think of what sort of probability distribution we're dealing with. So pause the video and try to solve this problem. Now that you have tried your best to solve this problem, let's see how it should be done. So I would like to remind you that we have 2 dice, and basically the probability distribution is not level. It is actually a triangular probability distribution because number 7 is most frequent combination of 2 dice. It could happen 3 and 4, 2 and 5, 1 and 6, 4 and 3, 5 and 2, 6 and 1. So actually 6 out of 36 possible combination. So it is the most probable expected value. So now let's move to a bit more complex case. So I would like to introduce you to the game of American roulette. It has 38 fields on which we can put bets on, and each field has payoff. And obviously, if our field that we have bet on it has not come up, we are losing all of our money. So here are the payoffs for the American roulette. For example, if we bet on a dozen, which means, for example, the second dozen here, all these numbers. So this is the first dozen, this is the second dozen, and this is the third dozen. So if we bet together on all these numbers, the probability of occurring this event would be 12 divided by the number of possible outcomes at the beginning, and the payoff, if we have a dozen, should be 2 to 1. So in a case of winning, we get 2 euros or $2. In case of losing, we're losing our only bet, for example, $1. So let's imagine that we have, let's assume that we wish to bet on a single number. Let's assume we wish to bet on, let's say, number 35. How do we calculate what is the expected value of such bet? We will have to start with outcomes. What are the possible outcomes? Outcome number 1 is winning. Outcome number 2 is losing. Okay. Second, we have to derive the probabilities for each outcome. The probability for winning is 1 out of 38 possible fields. So 1/38 is the probability of winning. And obviously the probability of not winning is the rest, all the rest possibilities, which is 37/38. So this is the second, we have the probabilities. And third, we have to compute all these things. So basically we have in 37/38 chance to lose our bet of $1 and 1/38 chance of winning our bet. In the case of winning, we get $35 for this bet. So this is the $35 here. And if we sum all together, so if we multiply it and sum it, we derive a result of an expected value of minus 0.05 cents, which basically means that we have a negative expected value. So what does negative expected value mean? It basically means that this is a losing proposition. On average, we're losing. This is what negative expected value means. So, let me give you an exercise for calculating expected value. You should now pause this video and try to compute what is the expected value of betting on the second dozen. So basically you have these 12 numbers out of 38 possible. Let's assume that you are going to bet $1. You have a payoff. In case of winning, you have a $2 payoff, and in case of losing, you lose your only $1 bet. Pause the video and try to solve it yourself. Okay, now that you have tried to solve it yourself, let us see what is the correct answer. Okay, the correct answer should be calculated as follows. First of all, we have a -1 in case of losing, multiplied by 2638, so 26 are all the fields that we have not bet on, out of 38 possible, plus 2, which denotes the possible earnings in case of winning, multiplied by 12, which is the number of fields we have bet on, out of the same 38 fields. And if we compute all this, we derive basically minus 0.053 cents expected value, which is first of all negative expected value. If you remember, this means that we are on average we are losing, so we may win on a certain occasion, but on average we are going to lose 5 cents for every bet. And second, it is very interesting that we can compare these numbers, and they're basically the same. Furthermore, if we try to compute what would happen if we are betting on, let's say, red, so all the red numbers, just for the sake of exercise, you can pause the video right now and try to compute it yourself. In case you have computed it correctly, you should derive basically the same way, and you should have derived the same number. Why? Although we have used different payoffs, different probabilities, we have derived the same number. Why? Well, just because the American roulette is the so-called programmed game, and it has hashed all its winnings and losing the same way. So it doesn't matter from the point of view of the casino how do you bet on average, wherever you bet, it doesn't matter when or where, on average you're losing 5 cents from every dollar. And this 5 cents, this number is an interesting term. It is called the casino edge. It is what the casino is legally allowed to benefit from each one's bet. And of course, I'm not trying here to persuade you to bet in roulette or in any type of casino game. Actually, on the contrary, I'm trying to convince you that betting on in a casino actually is a losing proposition, because all the games there are programmed so that you are losing on average. But at the same time, it is a good exercise, a good thought exercise, to try to compute expected value that way. So now, let us try to make some exercise with the probability distribution. We have a small tool here that we can change the probability distribution by moving a bar here. And basically what it moves is the dispersion. If we move to the left side, this bar, we have most of the outcomes forming a pile in the center of the distribution. And if we move it to the right, we have a bigger dispersion, bigger variance among the outcomes. So a quick question here. Which would be a distribution showing more risk? This extreme distribution, where we have basically most of the outcomes in the middle, or this distribution, where we have most of the, a lot of the outcomes spread around. Take a pause here again and try to think about it and try to come up with an answer. Alright, so now that you have tried and probably thought about it and probably you have guessed correctly, which is the riskier distribution, this one or that one, let us see what should it be. Well, basically the riskier distribution is this one. Why? Because we have a lot more variance and a lot more probabilities of different things happening. If we have this extreme distribution, we only have 5 different outcomes and each of them is relatively very probable. Whereas here we have many more different outcomes. Actually, we have 11 possible outcomes, and each of them have some probability of occurring. So the more spread the probability distribution is, the more risky the situation is. Using a similar tool for interacting with the probability distribution, we are going to implement another idea of quantifying risk, the so-called value at risk. It is a measurement, alternative measurement for assumed risk, which basically computes what part of the, let's say, invested sum in a given investment or in a business, or what part of the value of a given asset is under risk under certain circumstances. So what do we do here? We have 2 sliders this time. One moves the mean, so basically relocates the distribution, and the other is again sliding the dispersion. And then we have this shows us what sort of value is under risk. So obviously, if we move the whole probability to the left, so going into the losing, left is typically small number, negative number, and so on, into the losing part of the distribution, we are putting more of the probable outcomes in the losing column and under risk. And obviously, if we're increasing or decreasing the dispersion, we are additionally introducing additional risk. So another question here, which is better? There are going to be 4 cases here. I would like you to think about it. So when I show all the possible cases, think about it and pause the video, think about it, and try to come up with the best answer. Which is the least risky situation? Which is the situation where we have the least amount of value under risk? Okay, case number 1. We have minimum possible mean value of the distribution, and we have minimum possible of dispersion. This is case number 1. Case number 2. We have maximum possible mean value, and we have minimum possible dispersion. Case number 3, we have maximum possible dispersion and maximum possible mean value. And case number 4, we have maximum possible dispersion and minimum possible mean value. So think about it, take a moment to pause the video and answer which is the best option for us. Option number 1, number 2, number 3, or number 4. Now that you thought about it, you probably come to the right decision already. It is option number 2, which had the biggest mean value of the probability distribution and the least amount of dispersion as the best possible. Since it has the least amount of value under risk, you can see that the least part of this green value is under the negative part of the distribution. So, and finally, I would like you to think about it, about an alternative way to think about risk management and quantifying risks. It is called the idea of black swan. It is a book written by Nassim Taleb, a very popular author who actually argues that the using of probability distribution is not the right idea to manage risks when we are speaking about very extreme events. So what is the philosophy, first of all, when we speak about normal distribution or otherwise probability distribution? We are going to use, of course, as I already told you, symmetrical distribution. What is the typical thinking behind risk managers, behind looking at this distribution? Well, first of all, this is the most probable event. And we're going to prepare our company or our organization or whatever we are doing with mostly for this most probable event. Then we have, let's say, one statistical, standard statistical deviation distance, and all these are the most probable, statistically speaking, most probable events, and they are covering almost 70% of the outcomes. And we are going to prepare ourselves for all of them. Mind that we are going to prepare ourselves not only for the negative part, but also for the positive part of the risk. Okay, after we have prepared for this and we are ready to meet all these risky outcomes, then we move another statistical deviation further, and we are preparing for all these, not so many, another 27-28% of the outcomes. And when we have this, both of these zones covered for, we already have covered almost 95% of the cases. And in most cases, the risk management of any organization or every company stops here. Well, what happens in this case is that we have not prepared for all these unlikely events. And of course, if it is about winning, we really don't care because it is a very low probability, but even if it happens, it is something positive, so it's not really a problem. Really, the problem is here. The problem becomes huge when you think about it. We have not prepared for the really extreme rare events. And these are events such as terrorist attacks, events such as natural disasters, air crashes. All of them are less than 1 in 10,000 probability. And when they happen, when they occur, because nobody has prepared for them, there is a huge damage. There is a huge hazard out there. And these are exactly what Nassim Taleb calls the black swans. Black swans are basically extreme events that are negative in their nature and so rare that nobody has prepared for them. Why is it called black swan? It's an interesting story. By the way, I would like you propose that you read the book. And why black swans? Well, Europeans did not know that there were black swans existing on Earth before they went to Australia for the first time. It is, some 250 years ago. Up until then, everybody knew that the swan is a white bird. But it turned out that a special genetic mutation of the swans in Australia made less than 1 millionth of them black. And so it is a very extreme event and so on. This is how the Lab calls the extreme event. So I'm going to repeat this. Just imagine we have a matrix here, a risk matrix, an impact matrix, where we have probability of occurring a given outcome in one axis and the impact, okay, the result, and we are going to count the negative results here on the other axis. And there are basically 4 cells here. First is we have low probability and low impact, and in the extreme case we have basically no risk or next to no risk. So risk that we are ready to discard easily. Then we can have high probability event with low impact. So we are going to define this as a low risk. Next, we have a high probability, high impact event. This is a high risk event. It would be somewhere mentioned in our risk management plans, and we should be ready for it because it is a high probability event. And finally, we have the low probability, high impact, and it is a disastrous risk because nobody is expecting, and most of the risk managers are discarding the low probability events. And this is what black swan is. It is a low probability, high impact event. So, as a recap, I would like to remind you that there are basically 2 ways to look at events. First of all, likelihood of or probability of occurring, and the other is the impact or the level of damage or the level of result, of the magnitude of result that might occur. So what did we do in this part of the course, the quantitative aspects of risk? We have some knowledge now about how to compute expected value. Basically, this is the most important thing that I would like you to remember from today. Second of all, we know what the decision tree is. Third of all, we now know more about how to implement probability distributions of events within risk management context. And finally, we have some new understanding about risk measures such as value at risk, and we have new understanding about where the traditional risk management fails. It is at the so-called black swans, which are extremely rare events with a higher or large impact.